All right, so welcome to Math 409 problem solving lecture 11. So what I want to do is I want to do just a little bit more on the egg drop problem, and then I want to talk about Catalan numbers. So these were things you were supposed to be thinking about at home. Some of these questions are easy, some of them are significantly harder. And the goal is to just come to class prepared for conversations. So did anybody try to see if doing egg, doing two eggs together? Ooh, it's a huge thick connection. Okay, egg, and egg versus egg and egg. So the latter is what we did in class, where if we had 4 eggs, we dropped one, and as soon as that egg broke, we were then down to the case of having just 3 eggs. And in that case, if we do, say, every x for simplicity, worst case scenario, we would have to do n over x before the first egg breaks. And then for the second one, we now have x floors and 3 eggs. Does anybody remember roughly how long it took if you had 3 eggs? It was on the order of n if you have n floors and 1 egg, square root of n if you have 2 eggs and n floors. What was it with 3 eggs? It was, that was what, was it 2/3? I thought it was 1/3 for 3 eggs. Well, we know it's square root with 2 eggs, right? It can't be worse with 3 eggs. So I think what was 2/3 was how many floors you go before you drop. I think x was n to the 2/3. Yes. And then since we have n over x, that will be something of size n to the 1/3. So I think we get something like n over x plus x to the 1/3. And so if we just set them equal to each other just to get an approximate solution, this gives us n is about x to the 4/3. So x is about n to the 3/4. So the cost would be n divided by n to the 3/4 is about n to the 1/4. And so for k eggs, we would have roughly a cost of n to the 1 over k. Did anybody try to do egg versus egg? So my hope was maybe this does something better. So one solution, one approach is, as soon as the first egg breaks, I now have 3 eggs. But maybe it would be better to say, well, when the first egg breaks, I'm not going to let it get to me because I know I have a bunch of eggs left. And so maybe I'll take 2 eggs, keep working with them until both of those are broken, and then go on. So what I'm going to do with 2 eggs is I'm going to say, look, I'm going to group a bunch of floors together. The first B floors will be my first superfloor. Then the next B will be my next superfloor. So I will have n over B floors. So group blocks of B floors together. Okay. So how many superfloors do we have? So we have n over B superfloors. Does everybody understand this? Floors 1 to B is the first set, B plus 1 to 2B is the second set. With 2 eggs, I can determine which of the superfloors is bad. How many steps will it take me to determine which superfloor is bad with 2 eggs? On the order of what? So when we had n floors and 2 eggs, what was the cost? So how long did it take with 2 eggs and n floors. Right, but then when we optimized, how much was the cost? You're giving me how I got the cost. I don't care anymore. I just want the cost. Square root of the number of floors. So if we have n over b superfloors and 2 eggs, how many drops will it take to determine the bad superfloor? Well, I'm sorry? Root n over b. So we find the bad superfloor with 2 eggs in square root of n over b drops. Now, how many floors are left for us to determine? We've determined which superfloor is bad. How many floors are in the superfloor? B. So how many drops will it take, worst case scenario, with 2 eggs to determine which is the bad floor among the B superfloors? So this is the 2-egg problem now. So now it's the 2 eggs, B floors. So what's the cost? Square root of B. So total cost is the square root, that's total square root, is n over b to the 1/2 plus b to the 1/2. So we equalize, and that yields n over b to the 1/2 equals b to the 1/2. Therefore, if I square everything, I get n equals b squared. So b equals square root of n. So the cost is on the order of n divided by square root of n, which is square root of n, to the 1/2 is n to the 1/4. So same order. So unfortunately, if this method is an improvement, it's not going to be an improvement in terms of the power of n. It might be an improvement in terms of the constant. So I did not bother trying to think about that. So if anybody wants to and report back to the class, see if you can improve the constant by splitting it up like this. It is not the case that in every problem, whatever you try will always work. But this is not a bad idea. The first idea is, let me do locally what's best. I drop an egg, and as soon as the egg breaks, I now have 3 eggs, and it's the 3-egg problem. And the other one is, maybe I could just do 2 eggs, wait till it breaks, and then do 2 eggs for what's left over. Turns out it gives you the same order of magnitude in both settings. But again, the purpose of this class is to just introduce you to techniques. It doesn't work in this case, but this is not a bad way to think about things. Okay. Any other questions about the egg drop problem? All right, so what I want to do now is I want to do Catalan numbers and talk a little bit more about generating functions. So the Catalan numbers are defined as the number of paths from 0, 0 to nn that do not cross the main diagonal. So you can hit the main diagonal, but you can't go above it. So you have n steps to the right, you have n steps north, and as you walk, you've never taken more north steps than right steps. This is why another way of viewing this problem is it's the number of ways to put down left parentheses and right parentheses so that you've never read more right parentheses than left parentheses. It turns out Catalan numbers occur throughout mathematical physics. They have a tremendous number of combinatorial interpretations. They arise in diverse subjects from random matrix theory to graph theory. It's just absolutely wonderful how many different places they arise. So what we want to do is we want to come up with a formula. So was anybody able to come up with a recurrence for the Catalan numbers? So you're supposed to try to think about this and see, could you come up with a formula? The Fibonacci's had a really nice formula. Fn plus 1 was Fn plus Fn minus 1. Each object was essentially the sum of the previous 2, and then I give you some initial conditions. We did the M&M game with Cam and Kayla. And in the M&M game, we actually had a recurrence relation where we had two indices. So has everybody seen the Fibonacci numbers before this class? Okay, so everybody had seen recurrence relations with one index. Recurrence relations with two indices is a little bit harder. The Catalan numbers do have a recurrence with just one index, but it's no longer a fixed depth recurrence. So the Fibonacci is a depth 2. Each number is related to the sum of the previous two. The recurrence for the Catalan numbers, the further you go, the further down you go, the more terms are involved. So the Catalan numbers are going to be a lot more interesting. Talking about how to come up with the recurrence provides a great way to talk about how to calculate events. So we did the basketball game in this class, right? Bird versus Magic, first basket wins. What was really nice about this is it was very easy to split the probability of Bird winning into disjoint events. Bird could win on his. So how could Bird win? I'm sorry? Okay, be specific. Which shot? First shot. How else could Bird win? How else? And so on, right? So Bird is not going to win on both his fifth and eighth shot. There's going to be a specific shot associated where that's the shot that won it for Bird. So for the Catalan numbers, we're looking at all the paths from 0, 0 to NN, where you don't cross the main diagonal. Is it possible to go from 0, 0 to NN without ever hitting the main diagonal? So can you go from 0, 0 to NN without ever hitting the main diagonal? Okay, so we'll say, all right, we know you have to start at 0, 0, so all right. Is it possible to get from 0, 0 to NN without ever being on the main diagonal other than 0, 0? So you have to end at NN, so you have to end on the main diagonal. So there will always be a point on the main diagonal beyond 0, 0 where we hit. And so we can say, let's look at the first hit. So I don't want to use yellow. BK is the number of paths from 0, 0 to KK such that never hit main diagonal after 0, 0 and before KK. So KK is the first hit. And what we're basically saying is, if I look at all the Catalan paths, each path has to have a first hit on the main diagonal because we know they all end at NN, which is on the main diagonal. So some of them, that will be their only hit. Is it possible to have more than one way where NN is the first hit? Is there more than one way to have NN as your first hit? Yeah, if you look at the picture, you can see if I look at the first picture, the second picture, the third picture, all of them have NN as their first and only hit on the main diagonal. But if I look at the fourth picture, it hits earlier. And the seventh one hits at the same spot as the fourth one. So what I'm going to do is BK is going to be the number of paths. We'll plot it a little bit. So, here, let's say, I switched to eraser, okay. So here is 0, 0. Here is KK. Here's my main line. Now I know that I don't hit until KK. What must my first step be? Right. Must be right. What about my last step? Has to be up. And so now if you look at what's going on, the possible paths all have to be in this area. So let's see, if my daughter were here, she would do this. Shade this in properly. No, I don't know how to do it. She knows how to do it, I don't. All right. So all of the remaining steps have to keep us in this triangle, right? Because otherwise we would break the main diagonal. Can anybody tell me how many paths are there in this region? So we are starting now at 1, 0, and we're ending at k minus 1. So how many paths are there? Okay, so why ck minus 1?
Because this is a triangle with one smaller.
It's one smaller. We've lost one step to the right. We've lost one step to the left. The number of legitimate paths is just a Catalan number. So we know BK is equal to CK minus 1. Right? And so now if I want to calculate how many paths are there of length n, what are the possible values for my first hit? So I'm going to condition based on the first hit. Just like with the bird magic, I'm conditioning on what basket was the first one that bird made. I want to condition on the first hit. So what are the possible values for the first hit after 0, 0? And then what else? From 1 to n. I could hit at 1, 1, 2, 2, 3, 3, all the way up to nn. So k will be my index of the first hit. K goes from 1 to n. So if you think about what's going on, so here is my line. Here's 0, 0. Here's nn. And let's say the first hit here is at kk. So I have some path that gets me up over here. And now, how many paths are there in this window over here that keep me down here? So I have BK paths that take me from 0, 0 to KK. And now that I'm at KK, how many paths can I take from KK to NN? I'm sorry? Cn minus K. Because I've lost K left steps, I've lost K right steps, I have N minus K steps of each left over. I've got a smaller triangle. So this is just the same as the sum, K goes from 1 to N, of C, K minus 1, Cn minus K. Okay, any questions about this? So this gives us a recurrence relation for the Catalan numbers. If I have two paths that get me from 0, 0 to nn, each path has to have a first place where they cross. And so two paths that have different first places where they cross will be counted differently. So this is a nice way. So I now have my formula. All right, so I should be able to paste. Good. So here's my formula. Do we know any initial values? Do we know, for instance, what C1 is or C0? How many paths are there from 0, 0 to 0, 0? One. There's one way, right? There's one way to do nothing. If I ask you, what is the best TV show about nothing? The answer is no. Best TV show about nothing. Seinfeld. This is sad. How about C1? How many paths are there from 0, 0 to 1, 1? Where I don't cross the main diagonal until I get to 1, 1. 1. So it's actually not too hard to get the first two coefficients. If I wanted to do C2, that's a little bit harder now. I could do 2 steps right and 2 steps up. That's one way. Or I could do 1 step right, 1 step up. Then I have to go right up. There'll only be 2 ways. So it's got to be 1, 1, 2. 1, 1, 2. Now, of course, 1, 1, 2 is also how the Fibonacci numbers begin. So you might think, hey, maybe this is the Fibonacci's. But then you do the next one, you see it's 5, then 14, then 42. All right. So the question is, we want to solve and find what the CNs are. So there's a lot of different ways to do this. One way is there are a lot of direct combinatorial proofs. Can anybody give me an upper bound for CN? Or and a lower bound? Yeah, the lower bound, you can be a smart ass. Can somebody give me a lower bound for CN?
0.
0. Slightly better lower bound? 1. All right. There's at least one path. What about an upper bound? 2 and choose n. Right? Because we have n right, n up. The answer turns out to be Cn is 1 over n plus 1, 2n choose n. So 2n choose n is actually not that bad. And there's some really beautiful proofs. The Wikipedia page is actually very nice on this, talking about reflecting about the line and whatnot. I want to do the generating function approach because I really want to highlight generating functions as a technique. We saw an application of generating functions with the Fibonacci numbers. And that gave us Benet's formula, which gave us an explicit way to get a closed form solution for an arbitrary Fibonacci number. So we don't actually have to go through and calculate them term by term by term. So I think one of the problems I asked you to do for fun was to calculate if you were offered an A+ for your entire Williams transcript. If you calculate by hand the first million Fibonacci numbers, is it worth taking that deal? Can you do 1 million Fibonacci numbers in 4 years? If the entire campus worked on this, could you do it? What about 1,000? How many can we do? How long would it take you to actually compute? So you would need to know how many digits these numbers have. And we can approximate that. Each Fibonacci number is about 1.6 times the previous. You can try to figure out how many digit operations can you do a second. If anybody here can do more than 10 digit operations a second writing down, I'm amazed. I think 10 digit operations per second is very generous. And just see, could you get to 1 million in 4 years? What if the entire campus helped? Well, to some extent, how? Because when you're doing it by hand, you need to know what the previous one is. So maybe what you could do is maybe you have different people working on adding different parts of the numbers and then you bring in the carries later. I don't know. But I will assume that you could, if there are 1,000 people on campus, you'll put in faculty and staff. Oh no, well, sorry. Say 3,000 people?
Yeah.
Say 3,000 people. Everybody helps, from the president all the way down to the prospectives who are visiting. Everybody comes in. Give yourselves 10,000 people. Can you get up to 1 million? So that's a good exercise to do just to get a sense of the magnitude of the problem. All right, so what we want to do now is we want to talk about functions. So let's say fa of x is the sum, n goes from 0 to infinity of an x to the n. So this is the generating function attached to the sequence an. Okay. How many of you have taken probability? Have you seen generating functions in probability? So there's 3 different ones you can see. There's generating functions, there's moment generating functions, and then related to the characteristic functions. And so generating functions have a lot of remarkable properties. And so one of my favorite theorems if everything converges, the let's write, GA of X for FA of X, for generating function. I should have probably done that. And the generating function of A times the generating function of B is the generating function of C, where C is A star B is the convolution of the sequences. This means Cn is A0 Bn plus A1 Bn minus 1 plus dot 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 plus An minus 1 B1 plus An B0. And the proof is a direct calculation. So GA of X times GB of X is is A0 plus A1X plus A2X squared plus dot 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 times, let's use another color, B0 plus B1X plus B2X squared. B2X squared plus dot dot dot. And now let's start multiplying. So how can I get a constant term? The only way I can get a constant term is A0 times B0. Whoa. Okay, A0 times B0. Now, how can I get a term of degree X? I could have A1X hitting B0, or I can have A0 hitting B1X. So I can get A0 plus A1, and then this would be B1, B0, X. So is the pattern clear as to how you would get it? We're just basically saying, look, if I want a term of degree X cubed, then the sum of the indices has to add up to 3. So this is the generating function of two sequences. Okay. Why am I looking at this based on today's lecture?
Convolution looks like the recurrence relation.
Yeah, if you look at the recurrence relation for the Catalan, this is where I truly, truly, truly hate being the professor, is we have ck minus 1, c to the n minus k. That looks almost like the recurrence, right? What is the issue? What should it be? We want the sum to start at 0. We would want like ck c to the n minus k. So it's close, right? It's almost what we want for a convolution. And so the question is there a way to just tweak this a little bit and make it work? So let's paste it in. So let's change things a little bit. So we can shift indices. And so if we shift, we get Cn is the sum, k goes from 0 to n minus 1 of ck times Cn minus. So here we're using really bad notation. We're letting k equal k minus 1. K goes from 1 to n. Now k goes from 0 to n minus 1. Is this confusing, or people would rather have you use a different subscript rather than, let's use a different subscript rather than k. Let's use m. So we're letting m be k minus 1. So this becomes Cm. And now if m is k minus 1, we must have k is equal to m plus 1, right? So does everyone agree that this is what we would have? Yes? It is really easy to make a small mistake with the indices. I absolutely understand the theory. I also am, quite afraid that I will be off by 1 at some point in the calculation. But right now, this looks good. This is almost the convolution. I want Cm times Cn minus m. How could I rewrite this?
N minus 1.
Yes. So I then get Cn is the sum, m goes from 0 to n minus 1 of Cm Cn minus 1 minus m. And now it's a convolution. Right? If I wanted to convolve the Catalan numbers with themselves, what we're saying is the convolution is almost what you would want. It's just shifted ever so slightly. This would be the n minus first term. This would be the term of x to the n minus 1. And that's relating it to the x to the n. Well, if I just multiply the convolution by x, then that should match. So if I let C be the Catalan numbers, and I let GC of x be the sum, n goes from 0 to infinity of Cn x to the n, then GC of x should be GC of x times GC of x times x. Let me see if I got this right. Because the n minus first term in the convolution here is the nth term on that side. So when I multiply this out, and again, please, please, please tell me if I've made a mistake. This would just be a sum of, let's call it, I think it would just be Cn x to the n minus 1. N goes from 0 to infinity. So we've got to be a little bit careful about one thing. What do we have to be careful about? So when you look at this, when n equals 0, this is giving us like a 1 over term. Well, what would it mean if we're trying to use this formula when n equals 0? So if we have n equals 0, Cn is the sum, k goes from 1 to 0 of Ck minus 1, Cn minus k. So if we plug in 0, there's really no value of k that should work. Right? So how should we define C0? How should we define the number of paths from 0, 0 to 0, 0 that don't cross the main diagonal? I said before that we wanted to define it maybe as 1. Well, if we look at what's going on here, if I define that as 1, is this going to work? There's a constant term mismatch. And when I try to figure out what's going on here, these are going to be well defined, but I'm going to have the x's. I'm not going to have any constant term here. I'm going to have a constant term over there. And so when I'm trying to do this formula, I have a problem. But let's go back and think about what's going on when we look at the paths. If the first hit is when k equals n, then we want to multiply by C0. right? We don't want to multiply because if the first hit is at NN, there's nothing more to do to complete it. So we would want to just multiply that by 1. So there really is an incentive that we really do want C0 to be 1, right? So now when we're looking at this, we want C0 to be 1. But when we start looking at this and trying to match things, well, what would happen if we take C0 to be 1? It's the issue with C0. So we would want C0 is the sum, k goes from 1 to 0. Oh wait, of C k minus 1, C 0 minus k. So this seems to be giving us a negative index term that we would have to define. So we'd get, if C0 equals 1, or when k equals 1, we would get C0 times C negative 1. And then for the next piece, when k equals 1, we would get C0. I'm sorry, when k equals 0, we would get C of negative 1. And now k is 0, so we'd get C0. So we would get C negative 1 is, I think, 1/2. So do we want to have a negative first term? And if so, what will that do? So this is, you've got to be very careful with stuff like this. When I'm looking at my sum, k goes from 1 to n. I have this recurrence relation, but where does this recurrence relation hold? So where does this recurrence relation hold? N equals 1 or above. So it is really easy to have issues like this. So over here, I need to put in a little caveat. This needs n to be greater than or equal to 1. And this is one of the most common mistakes that happens when you do problems, is you write something down that's true most of the time in most situations, but it's not true everywhere. If I want to write down this recurrence works fine once n is large. What's the definition of large for this problem? One. So once n is a large number, like 1, then we know Cn is the sum of Ck minus 1, Cn minus k. And we have to define C0 to be 1. Because if we want this formula to work, once I am at Nn, there's nothing more to do. So if I want to multiply by something like this, I need C0 to be equal to 1. The question is trying to figure out, how do we fix things? So when we're looking at this formula is true for all values of n that are at least 1. Okay, so this is true if n is greater than or equal to 1. Okay, so what do we now have? Let me just copy this. So this is if n is greater than or equal to 1, and if n equals 0, what do we get? C0 equals 1. So we want to try to figure out what's going on. So if I look at GC of x, this is going to be the sum, n goes from 0 to infinity of Cn x to the n. And I want to compare with GC of x times GC of x. what's the constant term of GC of x times GC of x? Yeah, this is going to be C0 plus C1x plus C2x squared plus dot, dot, dot. What's the constant term? C0, and what does C0 equal? 1. So this is going to be 1 plus C1x plus C2x squared plus dot, dot, dot. When I multiply this out, it's going to be G of C star C of x. It's going to be the convolution of those two sequences. And it is going to match up. It is going to start off with a 1. But what about the next term? Well, what we saw is that the n minus first term of the convolution is equal to the nth term of the original function. It's shifted by x. So if we look at GC of x times x, do we agree that the coefficient of x here now agrees with the coefficient of x in GC of x? And the coefficient of x squared now agrees with the coefficient of x squared. What is missing now between this and the original function? They agree at x, they agree at x squared, they agree at x cubed.
It doesn't produce the C0 term.
It doesn't produce the C0 term. So how do we fix that? Add 1. So this equals GC of x for coefficients of x, x squared, x cubed, dot, dot, dot. So add 1. And so now what do we get? We get GC of x is GC of x times x plus 1. And now they work everywhere. Okay? So any questions on how we got this? So hopefully we've done this correctly. And now we have our generating function. And we want to find GC of x. Anybody know how to find GC of x? Quadratic formula, right? This is just x times GC of x squared minus GC of x plus 1 equals 0. This is your a x squared plus b x plus c equals 0. It's just a quadratic formula. So GC of x is going to be negative b. So what does b equal here? Negative 1. So negative b would become now 1, plus or minus the square root of b squared, which is 1, minus 4ac, minus 4x, divided by 2a, right? We now have the generating formula. So given the Catalan numbers, we got a closed form expression for the generating function. All we have to do is Taylor expand, and we have a formula for the Catalan numbers. Now, there's one slight problem here. We're supposed to find the generating function. Did we find the generating function? What did we find? We have 2 candidates. Shit. How do we determine which one is right?
In the limit, should approach 1.
Good. In the limit is what goes to what? Good. So as x goes to 0, the generating function has to go to 1. So we have 2 candidates. But the limit as x goes to 0 of GC of x is just the constant term, which is 1. Okay, well, if we take x equals 0, what do we do? Any thoughts?
just want it to be finite, both the numerator and the denominator have to go to 0.
So the numerator and the denominator have to go to 0. So if we take the plus sign, we're going to have the numerator is going to 2, the denominator is going to 0, it explodes. Has to be the negative sign. Must be negative sign, else numerator goes to 2 and denominator goes to 0. So we need 0 over 0, which is the only thing that can have a finite limit. How can you prove that the minus sign gives you the correct limit? L'Hopital, you know you've made it when your name is a verb. You L'Hopital it. So apply L'Hopital, and you get the limit as x goes to 0 of, let's do a GC with a minus sign, with a -1 to mean that's the -1 is going to be 1. So I'll leave that L'Hopital calculation to you. We've seen L'Hopital before when we're trying to come up with closed form expressions for sums of powers of integers. You know, I said we can actually bypass, we can prove that things are polynomial by using L'Hopital. All right, so we now know the generating function for the Catalan numbers is 1 minus the square root of 1 minus 4x over x. Or I can write this as 1 over x, 1 minus 4x to the 1/2 power.
It might have been 2x on the denominator.
It might have been. I would not be surprised. It is 2x. Thank you. So how do I expand this out? I want to write this as a sum. So I need to know what is the expansion of 1 minus u? It's 1 plus a1u plus a2u squared plus ... And for us, u will just be equal to 4x. So this is the generalized binomial theorem of Newton. So if you don't know the generalized binomial theorem, you have not lived. All right, and you need to remedy this. It's a beautiful theorem, but we can prove it by brute force. You know, roll up your sleeves and just remember Taylor series. So if I have f of x, that's going to give me the sum, n goes from 0 to infinity. Take the nth derivative at 0, divide by n factorial times x. I'll use u. Right? And that's how you get the coefficients. So an would just be the nth derivative at 0 over n factorial. So this is a senior seminar. We are supposed to be recapping things you've seen. Here's Taylor series. So let's start calculating derivatives. All right. F of 0 is 1. That's why I just wrote 1. F prime of u is going to be 1/2, 1 minus u to the -1/2. And then the derivative of 1 minus u is a -1. So f prime of 0 is just -1/2, right? F double prime of u is going to be -1/2 times -1/2 is 1 over 2 times 2, 1 minus u to the -3/2. And then I have another -1 coming out. So f double prime of 0 is going to be -1 over 2 times 2. F triple prime of u, I'll have a -2 times 2. I then bring the 3/2. 1 minus u to the -5/2. F triple prime of 0 is -1 times 3 over 2 times 2 times 2. Maybe there's a pattern. Maybe the next one is 1 times 3 times 5 with even one more 2 here. So find the pattern. So as a nice exercise to just think about is, find the pattern. There is a nice closed form expression for what these numbers are. And with a little bit of algebra, you will get the binomial coefficient for the Catalan numbers. All right, so this is a good place to end. Have a good rest of the day. Enjoy it. It looks like it is warming up nicely.